Bismillahirrahmanirrahim. Today we'd like to discuss on the continuous time Fourier transform. As I already have mentioned that this syllabus must have covered from different context of your different syllabus from last semester, even before. Even though I have found that there are some issues still inside the students and in their mind from the understanding point of view. So today my main objective is to represent the continuous time Fourier transform eventually to the discrete time Fourier transform. Continuous time Fourier transform, it leads to have discrete time Fourier transform. Conventionally, discrete time Fourier transform is known as the Fourier transform. So if you can understand the continuous time Fourier transform properly, you can understand the discrete time Fourier transform very easily. And eventually you can understand the Fourier transform. After knowing the Fourier transform, there is another topic called discrete Fourier transform, discretization of the Fourier transform. As we know that the Fourier transform is a continuous one. So discretizing of the Fourier transform is known as discrete Fourier transform. So they are very much related. So I believe that continuous time Fourier transform is very important to understand both mathematical perspective and as well as graphical with the graphical representation. During the session, if you have any question in any point, please do not hesitate. Please raise your hand so that we can discuss more on this topic, because this is a core part of our DSP. Okay, let me start with the expression. Okay, conventionally, when we are in the analog domain, eventually I used to use the omega as a capital omega and this omega as also capital omega. So the equation could be written in this way: f omega is equals to ft, that is the signal, e to the power j omega t dt due to the integration, and this is from minus infinity to plus infinity, where most of the cases we are using e to the power minus j omega t. I will explain each and every part of this equation as well as each and every part of this expression with the graphical representation. So you can use this expression as it is mentioned here. I have taken this lecture note from online sources. However, I will change it accordingly whenever it fits for understanding. So what is the difference between omega and this omega? This is capital omega. We have already mentioned it as the capital omega for analog signal, and small omega, this is for the discrete signal. That's why we will use this capital omega since we are in the continuous time Fourier transform domain. So this continuous time represents your signal. Your signal is a continuous one. That means ft is your signal, which is a unknown signal. And now what we are trying to do, we want to correlate our unknown signal with a known signal. That means if we have, let's say I have an unknown signal ft, I do not know what are the frequency component inside the ft. Then what we can do, we are multiplying our ft with e to the power minus j omega t. What is e to the power minus j omega t? This is nothing but cos omega t minus j sine omega t. So if I elaborate this part, I can write it in this way. ft multiplied with cos omega t minus j, I can take common of that, j ft sine omega t. Very, very simple. And then what we are doing the integration of the whole part, because both of them, that means ft and cos omega t or ft sine omega t, they are continuous in nature. That's why we are first operation, what we are doing, we are multiplying. ft is multiplying with cos omega t, and then we need to do the summation from minus infinity to plus infinity for the both cases, and then d omega, or sorry, dt, because we are multiplying for the time factor. In the left side, we are finding the frequency, which is a function of omega. For a particular value of omega, we have a different equation. For example, if I took, if the value of omega, let's say the value of omega is equals to 1 hertz, make it very simple. This will be 1 is equals to ft. What is ft? Unknown signal. You do not know about the frequency component. And then cos, this is 1. Omega is equals to 1, because we are looking for what are the component you have inside your ft of frequency 1 hertz. So make it very simple, though that is not 1 hertz. This omega is equals to twice pi f. So if I make it like this, twice pi, I should like capital F. This capital F represent the frequency. So for the simplicity, let's think that this is 1 hertz minus j, again ft sine omega is 1 and t, and of course there will be dt. This is from minus infinity to plus infinity. So now if I can write it more precisely, we can write in this way: f omega, we can divide in 2 parts, minus infinity to plus infinity, ft, that is your signal unknown, then cos omega t, write it here, dt, minus, there will be j, minus infinity to plus infinity, ft, then sine omega t dt. So mainly we have wrote this ft e to the power minus j omega t minus infinity to plus infinity dt. So we are actually elaborating this part as this part and this part, where the first portion can be mentioned as the real part, and the second portion is known as the imaginary part. So now if I ask you one question, what kind of operations we are doing here in to find out the real portion? What kind of operation? Any of you can mention that? What kind of operations we are doing? I'm talking about ft, then cos omega t dt, and making integration from minus infinity to plus infinity. What kind of operations we are doing? Have you ever seen this kind of operation in earlier segment? Of course, this is known as the correlation. We are doing basically the correlation between ft, where ft is an unknown signal, with a known signal cos omega t. Is cos omega t is a known signal to you? The answer is yes, because you know the omega value. By knowing the omega value, you definitely can understand what is the percentage of cos omega t inside the ft. In case of correlation, we can understand what is the similarity between a unknown signal to a known signal. What are the operations we are doing there? First, multiplication, then we are doing the summation. Of course, there is another operation called shifting operation. In this case, we are not making any shifting operation. Just think about this. Let's say you have an unknown signal which is known as ft, and another known signal which is cos omega t. So let's say this is your cos omega t. Now what we are trying to do, we want to multiply each and every point. If we target this mathematical equation cos omega t, what we are doing, we have ft and multiplying with cos omega t. So multiply each and every point. You need to multiply each and every point. So this is a point, you need to multiply it with this. This is a point, you need to multiply it with this value. So then you are getting a continuous multiplied value. After having the multiplication, what we are doing, we are making the integration, that means the summation, from minus infinity to plus infinity. That means that we started our signal with minus infinity to plus infinity in the time domain. We are doing all the things in the time domain. So whenever we are summing up all the values after multiplications, we are getting some number. Let's say we are getting a number a. If this a, that means the summated after summing up, this value is more than 0 or a is less than 0, that means you have some similarity. If the similarity is very high, that means a is very, very higher than 0. It shows that you have a higher component of cos omega t inside ft. If you don't have, that means if a is very close to 0, that shows that you don't have any component inside the ft. You don't have any component inside the ft. It shows that that frequency component doesn't stay or doesn't have any component inside your unknown frequency ft, and that is the Fourier transform for the real part. Similarly, for the imaginary part, we have ft multiplied with sine omega t, making the integration from minus infinity to plus infinity dt. Of course, there is a j. This j part just shows that this is the imaginary portion. Other than that, all the components are like the same as the real part. So as we have mentioned in this way, let's say this is your ft. Ft is any sort of signal, and now it will be multiplied with sine omega t. So of course, since this is a sine signal, it will start like this. What is the frequency of this signal? The frequency is omega, and that is why this signal is known to you. Now, what is our target? Our target is to find how much the known signal, that means sine omega t, is stay inside our ft. Okay, then what kind of operations we need to do? We need to do the correlation without the shifting. So we will make the correlation with a sine omega t, that means no phase shifting of the sine signal, with your known FT signal. And then you will find some value after doing this operation. Let's say you find a value B, JB, where B is the imaginary part. Now again, B can be more than 0 or B can be less than 0. In both cases, you can say that, okay, I have this component, sine omega t component, inside our FT. If and only if B is very close to 0, it shows that you don't have any component inside. You don't have any component of sine omega t inside the FT. So in that way, if I want to plot, like this, let's say this is the spectrum. This is the spectrum for A. So I'm drawing the amplitude of A for different omega. Let's say this is omega number omega 1, omega 2, omega 3, and so on and so forth. And this is of course omega 0, this one. And this is A, means for the real part. For FT as an unknown signal, I try to match with omega 1 real part. Real part means this is for cos omega t. I just match with those cos omega 1, cos omega 2, cos omega 3, cos omega 0. And I found that, okay, for cos omega 0, I got this sort of amplitude. For omega 1, I got this amplitude. For omega 2, I got this amplitude. And omega 3, I got this amplitude. What does it mean? It means that when I take FT and try to match with cos omega 0 t, doing this performance from minus infinity plus infinity for dt, then I got some kind of amplitude, let's say A0, and which is equals to, let's say, I got the amplitude A0 is equals to, let's say, 0.4. And here is that 0.4. This point is 0.4. When I have done the same performance for omega 1, ft cos omega 1 t dt, and from minus infinity to plus infinity for omega 1, let's say this is A1 is equals to, let's say I got 0.2, and this is that 0.2. Similarly, for omega 2, I got, let's say, 0.1, and for omega 3, I got 0.05. So from there, I can find that, yes, the FT is was an unknown signal. However, by doing this kind of correlation operation, I found that I have the cos component or real component inside of my FT, where the frequencies are omega 0, omega 1, omega 2, and omega 3. What about the other frequencies? There are different frequencies. They are continuous. It might looks like this. It might looks like this. That means you have a lot of frequency component. You have a number of frequencies. So you need to start with omega 0 and end up with infinite number. You need to start with omega 0. What is the value of omega 0? That is 0 hertz DC value. What is omega 1? It can be 0.01 hertz. So that means you need to try each and every frequency value to find out the real part, A component. So of course, this A is a function of omega. A is a function of omega, where omega is from 0 hertz, practically 0 hertz to infinity. You can start with 0 hertz and you can end up with a higher frequency. Definitely, you can also do it for a negative frequency, though that is only the concept. Similarly, what I have shown you we can do it for the imaginary part, and that is also a function of omega. If I want to draw it, this is the B value, the magnitude of that one for omega 0, omega 1, though that is a continuous one. Don't be confused with this notation omega 0, omega 1. Definitely you need to try in between as well, omega 2, omega 3. So for all the values you need to try. You need to try what? You will take your unknown signal multiplied with sine omega t, where omega, you need to change the omega. And for all the cases, you need to do the integration and make the summation. Basically what we are doing, we are, and after doing this, you may get this kind of amplitude in different section. Of course, that is a continuous one. It might happen that if you got let me give you this example. This is A and this is B. The magnitude response, whenever you are getting the magnitude response, that is nothing but real part square plus imaginary part square and root over of this. If that is so, the magnitude response shows that which frequency component you have. Let's say in case of omega 1, you have some value. In case of omega 1, in the imaginary, you do not have any value, like 0. Here you have the value, and what is the value? Let's say 0.5. Now, what is the magnitude response? Do you have any component from omega 1? The answer is yes, because you have 0.5 whole square plus 0 square and root over of it. So that means it is 0.5. You have the magnitude component, and that is 0.5. If you have something like this, omega 2, you have 0 there at the real part, but at the imaginary part, you have some value like 0.4. Do you have the magnitude response for that? The answer is yes. Again, the magnitude response for the omega 2, the magnitude response for the omega 2 is equals to 0.4. That means to find the magnitude response, you need both real part and the imaginary part to find out the magnitude response. If I now plot only the magnitude response for different frequency, and if I find this kind of response at a particular frequency, let's say 0 hertz, at 1 kilohertz, at 2 kilohertz, you do not have any other magnitude value. In all the cases, it contains 0, 0, 0, 0, 0, 0. Suddenly for 1 hertz, 1 kilohertz, you have some jump. How you got this jump? This is from A, 1 kilohertz. You have some value, square of that, plus B, 1 kilohertz, square of that, and then root over of this. It actually gives you this value. Similarly, how you got this? A, 2 kilohertz, square of that, plus B, 2 kilohertz, square of this, and root over of that. It gives this value. If this is the magnitude spectrum of an unknown signal ft, can you tell me what are the frequency component you have inside the ft? What are the frequency component you have inside ft? If this is the answer, magnitude response of ft.
0, 1, and 2 kilohertz.
Yes, 0 hertz, 1 kilohertz, and 2 kilohertz. And the significant part of this notion or representation is that ft was your unknown signal, and you tried all the possible value of A for all the possible value of B. From there, you actually try for all the possible value of the magnitude response, and you found this kind of spectrum. And from this spectrum, you can say that, okay, this contains, the FT contains 0 hertz, 1 kilohertz, and 2 kilohertz. If I sum up all the concept together, we can represent it that we have done nothing but do the correlation between ft with e to the power minus j omega t. We have done this correlation and summing up from minus infinity to plus infinity, where A represent the real part, where we are always taking cos omega t. This is a convention. And B is equals to sine omega t, which represent the imaginary part. And after having the real part component, real component, and the imaginary component, you can find the magnitude response. Okay, that is the full story of having the Fourier transform. Now, with some graphical representation. So this is the algorithm we have already mentioned. This is the algorithm where we are taking minus here and we are taking omega just to mention the analog frequency. Other than that, everything is the same. So it can be elaborated like this. We have also mentioned it. And you can also elaborate the whole thing in the two part, where this is the real part I have already mentioned, and this is the imaginary part. B, you can take this j out of the integration part. So now we'll try to perform these two mathematical concept with a graphical representation. Let's start with an example. Try to consider it as a general example. Afterwards, we can also give you some particular example. Here, this is a signal. This is our FT. This is our FT. So this signal, of course, this is a combination of few number of signals. For example, we are taking two signals and added together. The first one is a 3 hertz signal, which is a sine signal in a pattern. And here is the amplitude 0.6. The second one is a 8 hertz signal. The pattern is a cos pattern. And this is the amplitude is 0.8 hertz. So arbitrarily, we have taken this signal. You can take any two signals to produce your FT. Now the thing is, from this signal, is it a known signal to you or unknown signal? For this example, this is a known signal, but eventually this should be an unknown signal. So since we know that, we can expect that after doing the Fourier transformation, we are expecting that there should be a 3 hertz and there should be an 8 hertz component we should found out of this unknown signal FT. That should be. And whenever we'll find the 3 hertz signal, that should be a pattern of sine. And whenever we'll find the 8 hertz signal, that should be a pattern of cos signal. Okay, let me start the process. So step number 1, what is the step number 1? The step number 1, you need to do the multiplication. So before that, you need to put it in the time domain. Let's say this is FT, and on top of that, we are taking the frequency 3 hertz cos twice pi into 3 into t. Okay, that is the signal. We just let, we are taking ft. Which one is ft? The black line is the ft. Try to understand each and every part. And where is cos? Twice pi f, where capital F is equals to 3 hertz. Where is that? This green line is cos twice pi 3t, where we are just targeting that our frequency, analog frequency is 3 hertz, and that is a cos pattern. The lower portion, where again ft, the black line is your ft, and sine twice pi 3t. Where is that? The red one is the sine 3 hertz signal. So this is the step number 1. We are just put those two signals in the time domain. Now, what is the second step? We need to multiply each and every point. We need to multiply each and every point. Let's see how it looks like. This is the multiplication. As you can see, any point, if you are taking any point, you can multiply. For this one, we have some positive value. We have some positive value. So the amplitude would be a positive one. For this line, we have positive value for the ft and negative value for cos part. So that's why if you multiply it, you got a negative value. For this point, we have 0 for ft and some negative value for so 0 for ft and negative value for cos. So 0 multiplied with some value, it will give you the 0 value. Similarly, we got 0 here. We got some positive value. We got some positive value. We got negative value, negative value, negative value, and positive value. So the red dots, what I am mentioning here, these are the, sorry, just a minute. The red dots represent the multiplication point. Now my question is, since both of the signals like ft and cos twice pi 3t, both of them are continuous, of course you will got a continuous output, continuous multiplication output. Similarly, for the sinusoidal multiplication, ft multiplied with sine twice pi 3t, when you are multiplying the things, you are not only getting those single points, not only those points, you are also getting the points for each and every portion. For each and every portions, you are getting the multiplications result, of course, because this is a continuous data. So when you have multiplied it, eventually you'll get this kind of result. I'm talking about this result. So you'll have a continuous result for the multiplication. Okay, so you'll have this kind of result. Since ft and cos omega t, they are continuous, you'll got this continuous result. Okay, you'll got this continuous result for each and every portion. Now, if you, so this is step number 2. So step number 1, you are putting ft and cos omega t and make a multiplications. And in step number 2, what you can do, you need to sum up all the areas. You need to sum up from minus infinity to plus infinity. All the areas you need to sum up. So if you summing up all the areas from our naked eye, we can say that, okay, this will cancel this will cancel this, like this. So the higher value, the positive value, the negative value, positive, they are almost equal. So they are actually canceling each other. That means we do not have the summation. The summation gives almost zero value. And that is expected. Why? Because as we have taken our FT, what was our FT? 3 hertz sine signal and 8 hertz cos signal. So since we try it with a 3 hertz cos signal, it will not be matched. So we found that the real part for 3 hertz, it belongs to very close to 0. The amplitude for the real part for 3 hertz, we got it very close to 0. Okay, what about the imaginary part? Imaginary part, that means 3 hertz sine signal. Unfortunately, we already know that our unknown signal already contain a 3 hertz sinusoidal signal. So that's why we found that eventually the summation, after doing the summation, they are not canceling each other. You have lot of plus component. You have lot of plus component in the upper side. We have lot of areas in the upper side comparing to the lower side. So that's why this summation, I can write in this way, B3, this is higher than 0. That means it contains some value. It contains some value means you have some magnitude in case of sine, twice pi 3t. So you have some value. But in case of cos 2 pi into 3t, you are getting the value very close to 0. If we proceed more, now we have tried it for 3 hertz. Now, if we try it for 5 hertz, what is our expectation? What is our expectation of A5? What is our expectation? Should we get any response, any similarity?
No, sir.
No, because the FT is a combination of 3 hertz and 8 hertz. Whether this is a sine or cos, there is no 5 hertz signal inside the FT. So that's why we are not expecting any A5 or any B5 as well. And we can follow the steps. What is the step number 1? FT, always this is your unknown. And now this is cos twice pi into 5t. Do the multiplications and make the summation from minus infinity to plus infinity. And from viewing the areas, you can again found that there is 2 negative that will cancel to positive. Again 2 negative, you have 2 positive. Positive, negative, positive, negative, and negative, this positive. They will cancel each other. And in by using the MATLAB, you can do it yourself and you will find the same thing. I have done myself and I can observe that, okay, it is a real fact. So ultimately you will find that the amplitude A, real part, for the frequency 5, it is very close to 0. Eventually it is equals to 0. Similarly, for sine 5 hertz, you will have the magnitude, the imaginary part, it is also close to 0. Ultimately it is equals to 0. You'll find that this part, they will cancel each other, and eventually this part. So small segment and the large segment, they will cancel each other. So you'll find that the magnitude response for the B5, that means 5 hertz sinusoidal signal, you will have the summation from minus infinity to plus infinity, gives you very close to 0 value. Okay, now we try the 8 hertz, and eventually we can expect that since our signal was the cause signal was 8 hertz signal, so we can expect, yes, that A8 we should get some data more than 0 plus, and we have found that this summation in the summation from minus infinity to plus infinity, we got a lot of plus amplitude. We got this. So if you sum up from minus infinity to plus infinity, of course, the A8, the magnitude, the real part would be more than 0, which is expected. However, in case of sine, that means the imaginary part, B8, that is very close to 0. Even though in the FT we have an 8 hertz signal, but that is not a type of sinusoidal, that is not a type of sine signal, that is a type of cosine signal. That's why it match with the cosine signal. And in case of sine signal, it is very close to 0. And this is how we can understand the response of a signal. Now we have tried it for 8 hertz. Now if you can try it for 30 hertz, what is our expectation? The expectation A30 should be very close to 0. What is our expectation in B30? What is our expectation?
Very close to 0.
Of course, very close to 0, and eventually that is 0. So that means we should start our frequency, try our frequency from actually 0 hertz to infinite frequency. Any frequency you need to try. But in practice, there should be some limit. Okay, whenever we got eventually the 0, 0, 0, 0 all the way, then we can stop counting. But whenever you have an unknown signal FT, we need to try with our frequency F. Our frequency, or capital F, is equals to from 0 hertz cos signal as well as 0 hertz sine signal. Whenever you are taking cos signal, you are getting the real part, and whenever you are taking sine signal, you are getting the imaginary part. Both A and B parts are very important to find out the magnitude response, because whenever you have only B part, it also gives some magnitude value. Whenever you only have a B part, that also give you the magnitude value. Eventually, if you have some magnitude response like this, high value like this, ultimately, in the current example, we have 2 peaks. One should be at 3 hertz and another one should be at 8 hertz. And it shows that we have 3 hertz component and 8 hertz component inside our unknown signal FT. That is our finding. And how do you found this? This is a component. This is like sinusoidal, or whether this is a causal signal. It depends on whether you got this magnitude response from A part or you got this magnitude portion from the B part. Eventually, it gives you the overall magnitude response. I'll talk about the A and B part more whenever we'll talk about the phase response of a system. For the magnitude response, of course, A square plus B square root over that gives us the magnitude of that frequency. More specifically, we can write it is a function of F and B square. That is also, sorry, the B. That is also a function of F, and it can be written as the magnitude is a function of F. For each and every calculation, we have changed the value of F and tried it for both A portion and the B portion. And after that, we have found the magnitude part. So we have tried it for the 30 hertz. Now, with a different, okay, up to this, do you have any question or any comments? Okay, it seems that you understand the portion. Okay. Now the unknown signal looks like this square wave. This is the unknown signal. This square wave is the unknown signal. Now we need to find the continuous time Fourier transform of this unknown signal. So again, the steps are the same. By observing this square wave, can you find the frequency of that square wave? This is from 0 to 1 second. 0 to 1 second. How many pulses you have? You have 1, 2, 3, 3 pulses. So what is the frequency of that square wave? Can you count that frequency of that square wave?
3 hertz.
3 hertz. So in 1 second, you have 3 full cycle. So that is a 3 hertz signal. Okay, whatever the thing, we tried it.
Isn't it
Sorry.
2.5 hertz? So isn't it 2.5 hertz?
2.5
frequency. Yes, sir.
This is the total time frame is 1 second, and you have, if you start with this is a full cycle 1, this is 2, and this is eventually 3. So we have 3 cycle, almost 3 cycle. So that's why we can say that, okay, this is a 3 hertz pulse wave. But inside the pulse, this kind of pulse signal, as you can know that there are a lot of other frequency component. Though the 3 hertz will be dominating, however, there are some other frequency component as well. Okay, and let's see how we can find those frequency component. So step number 1, we have our ft multiplied with cos twice pi. What should be the frequency? Any frequency. Let's try it with 3 hertz. Just arbitrarily, we are putting 3 and t. So we have that cos signal. We have plotting this cos signal in the time domain. And the second step is you need to multiply. Whenever you are multiplying the things, you can see that whenever this is a positive portion in the cos and there is a negative portion in the square wave, so definitely the multiplication values are being a negative value. Whenever both of them are positive, then you will got a positive segment. This is a positive and negative. That's why this is a negative segment. Again, you have a positive segment and you have the negative segment there. So if you add all those things, positive and negative, what is the expected value A3? More than 0 or less than 0?
Less than 0.
Less than 0. So that is A3 is less than 0. Eventually, there is a match. Is equals to 0 means there is no match. If I have A3, let's say A3, sorry, not minus 3, A3 is equals to minus 0.55, which is here, minus 0.55. Whenever I make it a square of that, definitely you got the magnitude portion from there. That's why it is very effective in a way that eventually you are getting a negative value, still you have the value. So you have the A3 is equals to minus 0.555, which is a very higher value. Similarly, for B3, you got this value, which is 0.31614. So you have both A and B part. So if I try to find M3, it is equals to A squared 3 plus B squared 3 and root over of that. And you will got some magnitude response, and eventually that value is very high and very close to 1. That means a huge portion huge portion is of FT is matched with the 3 Hertz frequency component. Okay, at this moment, if I ask you, it's a very simple question. If I shift this the pulse wave to the left, if I shift my pulse wave to the left, do you expect any change in the value of A3?
No, sir.
Try to observe it very precisely. Let me draw it in different color. Let me draw it in the red color. So if that is shifted to the left like this, it might be looks like this. I'm shifting my delta the pulse wave to the left. The cause wave still remain the same because all the time we are taking cos 2 pi then 3t, where what is the phase of cos twice pi 3t? Always the phase start with 0. 0 means it will start like this, like a simple cos wave. So that's why it is not shifted. But I have shifted my unknown signal FT little bit to the left. So if you now multiply each and every point, what would be the value?
Goes to 0.
Well, let me give you this example because this is very important. First of all, let me draw the pulse wave. This is 3 Hertz. And see that. I made some mistake. Let me choose another color so that one pulse of the cos signal will contain the full portion of that one. Whenever this is the case, then whenever you are multiplying the value, you'll find that for half of this, for this one, what is the multiplication result? Plus and plus, that will give you a plus value, and half of the cycle, there is a positive, the black line, and negative, the green line, that will give you the negative value. Similarly, for this one, you have negative value and negative value, that will give you a positive value, positive amplitude. And here we have a positive value and negative value. Eventually that will give you a negative value. That means you have a positive outcome there, positive amplitude, and you have a negative amplitude there. Again, there would be a positive outcome and there would be a negative outcome. Here we have both positive, that's why there will be a positive outcome, and there is a positive and negative, there will be a negative outcome, and it will continue like this. That means this positive and this negative, they will cancel each other. Positive, negative, they will cancel each other, and ultimately you can expect A3 is very close to 0. If I can go back to this, you'll find it here. If you concentrate it here, you'll find that there is a very small positive portion, negative portion, positive portion, negative portion, positive, negative. And that is why you are finding A3 is equals to a negative value. Now just think that what I am telling, if you shift this square wave little bit to the left, in that case, of course, this positive portion will increase more, isn't it? Yes or no? If you shift your square wave a little bit to the left and eventually to this portion like this, in that case, the whole bunch of portion will works like a positive value. And the other portion works like a negative one, because negative multiplied with a positive will give a negative value. I'm not sure about this. If you shift this square wave a little bit to the left, it will increase this value more, isn't it? This positive value will increase more if it is like that. Let's say if this is like this, what will happen? That will also carry this whole portion as positive, this portion as positive, this whole portion, and this portion as negative. Negative portion may be mentioned as black line. So the positive portion will increase and the negative portion will decrease. And in some point, if I took it like this, in that case, what will happen? The half of the portion that will carry full positive, and half of the portion that will carry full negative. Are you agree with me?
Yes, sir.
If it is not clear, please draw it yourself and you will definitely find it very simple. What I am meaning that whenever this square wave is shifting to the left, what happens? The value of A will change, definitely. And in some moment, it might happen that A3 is very close to 0. However, in that case, of course, this delta, that means this square wave is shifting more to the left as well for the sine function. And eventually what you will find all are positive. The positive portion will encourage. The positive portion will encourage more rather than negative portion. And you will have almost all the positive value over there. And eventually you will find B3 is very close to 0.9. Let's say 0.9. I believe that you understand the point. Whenever we are shifting this square wave, it will encourage some value, whether it could be real part or imaginary part. But ultimately, the magnitude response will remain the same, because the magnitude response depends on the square of real part and square of the imaginary part. Now the question is, then what is the significance of the real part and the imaginary part? You can find that the phase shifting of the FT, that means your unknown signal, whenever you have shifting your phase, in that case, of course, the ratio of A and B will also changes. In this point, I can give you a very simple example. Let's say I have an unknown signal. This is my unknown signal. It looks like a cos wave. This is my unknown signal. What is the frequency? You can think any frequency of that. Now, what is the first step? This is your FT. And now what you are doing, you are putting a cos wave on top of it. Maybe the magnitude is different, okay? Just to make you understand. This is my cos wave, known frequency. Since they are the same frequency, fortunately. Now, what is your expectation? Let's say the frequency is f is equals to 3. So what is your expectation of ft cos twice pi 3t, summation of that from minus infinity to plus infinity dt, which is nothing but a3. What is your expectation? The amplitude. What is your expectation? Very high or very low?
Very high, close to 1.
Very high, close to 1, and equals to 1. It should be, because all the cases you can find that whenever you are multiplying the thing, whenever you are multiplying all the cases from 0 to this point, you have a positive value. From this point to this point, you have again positive value, because negative a positive. You'll get a positive, you'll positive, all the way you are getting whole positive value. And if you do the summation from minus infinity to plus infinity, you get the whole bunch of things. Basically, we do the averaging of that. We are making an average, and eventually this is equals to 1. A3 is equals to 1. Now, if I just remember that A3 is equals to 1. Now, if I draw the same thing again, this is our unknown signal. It looks like a cos signal, as we have mentioned earlier. And now we are taking a cos sinusoidal signal, sine signal, with the same frequency. Just our target is to find a B3. What is B3? B3 is nothing, ft sine twice pi 3t dt, integration from minus infinity to plus infinity. So whenever you are multiplying those two, let's say for this portion, let me choose another color. For this portion, what is the multiplication value, positive or negative, from 0 to this portion? What is the multiplication value?
Positive.
Positive. From this point to this point, what is the multiplication value? Again, positive. From this point to this point, this is negative, because one is positive, another one is negative. So you have a negative one, negative value. For the other portion, up to this, two of them are negative. That's why we have positive. One is positive, another one is negative. We have a negative one. And from this one, we have positive. From this one, eventually, positive and negative, we have a negative one. So if you go through, you'll find that the positive and negative, positive and negative, positive and negative, they will cancel each other. And eventually, you will get B3 is very close to 0. That means you already have A1 is equals to, sorry, A3 is equals to 1 and B3 is equals to 0. Now, what is the magnitude response? Of course, the magnitude response is equals to 1. 1 square plus 0 square root over is equals to 1. But what about the phase? Phase is equals to nothing but tan inverse B by A, imaginary part over the real part. And what is that? Tan inverse B is equals to 0 divided by 1. That is tan inverse 0 is equals to what? Tan inverse 0 is equals to 0. That means the phase is 0. Phase 0 means it looks like a cos signal. Your unknown signal ft, you can present your ft in the magnitude response. This is a magnitude response m. What was the frequency you have found? You have found that this is a 3 Hertz signal. You'll got a peak. But what about the phase? The phase response. You have found that the phase at 3 Hertz, it is 0. 0 means what? The phase at 3 Hertz you got, it is equals to 0. 0 means it is like a cos theta. Now eventually, if your ft, that means unknown signal, looks like this. Now try it yourself. If you shift your unknown signal a little bit to the right, and if it looks like this, if your unknown signal now looks like this, neither like a full cos wave or neither a sine wave. What is your expectation of now? What is your expectation of A3 and B3? What is your expectation?
A3 less than 1 and B3 greater than 0.
That means you will have some portion of A3. For example, let's say it is 0.7 and this is 0.3, just to make it very simple. That means A3 will decrease and B3 will increase. And eventually, when your unknown signal is proceed and looks like a sinusoidal, so how we got this? Previously, it was like this. So we start with this portion. Now we start with this. So our signal is now looks like a sinusoidal signal, sine signal. Now, what is your expectation? A3. What is your
0.
expectation? What? Please.
0.
0. And what is your expectation? B3
1.
is equals to 1. If you got A3 is equals to 0.5 and B3 is equals to 0.5, then what is the phase of that signal? What is the phase of that signal? You can find theta is
45
equals
degree.
to, yeah, tan inverse B by A, where B is equals to 0.5 and A is equals to again 0.5. So that means it is equals to tan inverse 1, and that gives 45 degree. That means the cos signal shifted for 45 degree positive.
Sir, will the magnitude value change from 1?
Yes, could you please repeat again? What is the question?
Sir, at first, without the shift, the magnitude value was 1. As we shift the values, will the magnitude value change?
Magnitude value of what? The unknown signal?
Magnitude value, magnitude response at 3 Hertz of the unknown signal.
No, the magnitude response will not change, because the total magnitude response is again A square plus B square 3 root over of that. Sometimes this will shift it, that means decrease. Similarly, the B part, the real part, the imaginary part will increase. So by the change of both, they will make a balance and the magnitude response will remain the same all the time, since your FT, the unknown signal, is not changes.
So, sir, the 0.5 and 0.5 value combination is not possible then.
Okay, this is just this is an example, just an hypothetical example. Okay,
sir.
of course, the magnitude, this is very good question. Of course, whenever you have your FT, whether FT is shifted for some samples, let's say in the time domain, if I shift it like FT minus 10 for 10 seconds, or this is FT plus 10, whatever the thing, the shifting operation only make some response to the phase of that signal, not to the magnitude of that signal. You have unknown signal FT, it can be shifted for 10 seconds in the positive direction or 10 seconds in the negative direction. In the both cases, the magnitude response remain the same for all the frequency component because you are not changing the frequency component. However, in case of phase, the three phases of three, so the phase will be changes for three different cases. And eventually, for three cases, the value of A and the value of B will changes in such a way so that the magnitude response remain the same, but the same phase response will change accordingly. Okay, is that clear?
Yes, sir.
Okay. Okay, so again, so I believe that you understand what is the significance of A and B from the phase point of view. This is the same thing we have continued. If it is if the frequency we have checked it for 6 Hertz, still we have some A component and the B component, though the values are very small. So it shows that we have the 3 Hertz component as well as, sorry, 3 Hertz component as well as we have 6 Hertz component, though the 6 Hertz component has a very small impact to your unknown signal. Now, this is a very simple example where we have a signal, unknown signal, and this is the real and imaginary. The real mentioned as the green line and imaginary represented by the red line. And from there, can you find what is the frequency component inside your unknown signal? This is in Hertz. This is in Hertz. What is the frequency component of this unknown signal?
40 Hertz.
Exactly, 40 Hertz. We have both the real part and the imaginary part. It shows that it is not like a cause or sine. They have some phase shifting as well. And here the phase shifting also shown by this. I will talk about this phase shifting later on more specifically, because all the phase shifting parameters are not real component. That all the phase shifting component doesn't mean anything for all the points, for all the frequencies. Just only that point where the shifting has been done for the phase operation. Okay, we'll talk about this later on. However, this is very simple to understand that we have this real part and also the imaginary part, and we have both the real component and the imaginary component. That shows that we have both A and B for 40, and this is also for 40. And since we have the significant part, we have some phase shifting as well. We can find it by using the tan inverse.
So is this theorem alright?
Tan inverse operation, and about the magnitude response, A square, B square, and plus of that and root over of this. That will give us the freedom to find out the magnitude response. Okay, another one is this. This is our FT. That means unknown signal. Now it is not very much known to us what would be the frequency component. So if you follow the same steps, you can find ultimately this is the magnitude response. Okay, this is the magnitude response. From the magnitude response, we can easily find out that the frequency component inside this FT, we have the 0 to almost 30 or 30 plus minus. So 0 to 30 hertz is the frequency component of this FT, the unknown signal. And both the real part and the imaginary parts are shown here in this segment. One more question. If you have your FT looks like this, let me now the size is actually doubled. Let's say the size is double. Previously, what was the width of FT? Now the width of FT is double. Can you expect what would be the magnitude response? That means what are the frequency component you can expect after doing the Fourier transform? Previously, the FT was like this. Now the FT is more flat. Let's say the width is now double. What is the expected frequency?
So the same frequencies, but twice the magnitude.
Any other guess? Okay, probably you can give this answer very easily. If I have a sine signal like this, what is if the frequency is 3 hertz in the magnitude response, if I have the sinusoidal double of the area it covers, then what was the frequency you are expecting?
Oh, sorry, it should be half then, the frequency?
It should be half. Then this is 1.5. So your answer should be like, if the band was like 0 to 30 previously, now for a flattened signal like this, it should be from 0 to 15. So you are expecting close to 0 to 15 hertz. Okay, this is just a general question. And this sort of FT is known as hat signal. This actually looks like a hat, isn't it? If you just consider this part, it looks like a hat, cowboy hat. Okay, so that's why this is known as a hat signal.
Sir, when the signal is broadened, the frequency becomes half. Any changes to the magnitude, or the magnitude remains the same?
It depends on the magnitude as well. You need to perform the magnitude response, and then you can say something on the magnitude response. It's very straightforward. It's difficult to say what would be the magnitude response from the magnitude point of view. I'm just talking about the component, frequency component. Okay.
Okay.
Okay. Now your responsibility is to play with this. Choose some FT. How you can choose that? Take two signals, any two signals, and added those two signals, and after that try it for different frequency. You already know the frequency, so I'm talking about this example. So we have already shown this example, the first example. So try the first example. This is very easy to understand because we have already told you. So draw it in the MATLAB and try it for different value and find the area and try to understand step by step, so that you can understand each and every point. So in the next class, inshallah, we'll talk about the discrete time Fourier transform. That is nothing but the improved version of the Fourier transform, continuous time Fourier transform, where we are using, in case of continuous time Fourier transform, we are using FT, or you can say XT, where this value is a continuous one, However, in case of discrete time Fourier transform, we'll use xn as the input unknown signal, and we need to find the frequency component of that signals. I have taken a bit longer time, okay, since we don't have any other class today. Okay, do you have any question? So I'll request you for several times that please go through this lecture. This is one of the important lectures during the whole semester. If you can understand this portion, continuous time Fourier transform, by your heart and by graphical representation, both mathematical representation, I believe that will definitely help us. And I expect some question in the next class on this topic if you have any problem to understand this. Okay, thank you for your presence.
Inshallah, sir.
Thank you for your presence.